Day 2 of CES, and this is special. We're here with TactoTek. We're gonna peek under the hood, and we're gonna look at some of the really cool stuff that you guys are working on. So, we've been working with TactoTek for a while. We've got this really cool Nighthawk demonstrator, but we have a whole bunch of other toys in front of us that I want to hear about. Who wants to go first?
Hi, John. Great to see you again. I'm Dave Rice with TactoTek, and we have a number of demonstrators that are spread out on the table here. A lot of them feature illumination. Let Light Live is one of our themes with IMSE technology, and that's in-mold structural electronics, where we're integrating printed electronics, electronic components, and into single injection molded three-dimensional structures. Of course, there's even more that we can't show.
Of course.
But we have some really exciting things to show today. One of them is this Mesa controller. And on this controller, each side of this raised element is a slider. So I can have single touch and multi-touch gestures. And you see here how the colors are changing, showing that a touch event is recorded. Of course, we can use that to navigate menu structures, to make it very easy to perform complex tasks, whether it's on a center console control of a car, or maybe even on a dishwasher.
Correct.
So really exciting. This eliminates 70% of the plastics relative to a conventional electronic structure. And it does so in a solution that's only a few millimeters thick. We have other parts over here, including Passive Bolt's Shepherd lock cover. And as you can see, it has capacitive touch and illumination integrated within that smart lock cover. We have illuminated logos. Those are becoming very popular. It's a simple use case for in-mold electronics, but it's very powerful because now we can have those types of bright, even illumination in a structure that's only 2.5 to 4 millimeters thick. So it can be put almost everywhere. It makes integration easy, and the tooling is very straightforward as well.
Now I have to step in here because the key point that I want to explain or reinforce is the fact that in order for light to be used as a language, as a communication method, we need a transparent element. And this is what makes me very happy because now we're talking polycarbonate. Now we're talking polycarbonate not just for the structure, but also for the clarity that allows the light to shine through, right?
It just both allows it to shine through, it allows it to be bright and undistorted. So as in the Nighthawk demonstrator that TactoTek and Covestro partnered in creating, we have a display behind there. And that display is crisp and clear and controlled by the capacitive touch functions. And you can easily envision different home automation features, home appliance features for which it would be a natural.
All right, now, Pavel, walk us through how you guys built this really cool stuff.
John, like you said, polycarbonate is key ingredient on IMSE stack, and I will walk you through how we build IMSE part.
Cool.
So we start with the polycarbonate substrate, where we print graphic inks and conductive inks. These are silver-based inks which enable the electrical function for the part. We go for the second step, where we mount components by utilizing surface mount technology on the substrate. For example, here we have LEDs, as well as our system in package, SiP, which enables the digitalization of plastic in the end. The third step is high-pressure thermoforming, where the IMSE magic starts to happen. We have a tool underneath, high pressure, high heat on the top, and then the film elongates, the silver flakes move a bit, and we are able to create truly 3D shape on the part.
And what about the connector?
The connector is crimped here, which will be overmolded later on to create the interface for the other part. So now we have the functional polycarbonate film with conductive inks and components, and then we have a polycarbonate film with graphics. We insert both of these into the tool and injection mold the polycarbonate resin in between. It goes here, and in the end, we have the IMSC.
Beautiful part.
Yeah. So polycarbonate films with polycarbonate resin, conductive ink, and components, enabling digital plastic.
I am absolutely in awe. And then you power it up, and it comes alive.
Yeah.
And that's the part that has blown me away. Now, in addition to the light, this one has even more features.
Yeah, it has haptics on it. So just not only the capacitive functions, but true haptics feeling.
And by haptics, we're talking feedback. Your hand, I've played with this before and I was blown away. Your hand actually feels like something's moving.
Yeah,
it's
right.
not just the light, it's not just the sound.
Yeah, tactile feedback when you press.
You know, because these IMSC parts are light and they are single-piece structures, they're easy to move. And so haptics manufacturers, companies that specialize in haptics, really are drawn to IMSC technology because their own user interface benefits can be shown to really great advantage. This one is done by one of our partners, and they took a standard IMSC part, and there's even a selectable set of effects. So you can have it with beeps and audio to have that audio reinforcement of the tactile effects. Or you can just have different tactile effects and tune them so they feel best to you. And you can see that even if this were put in a car or if it was put on a washing machine, you could allow the user to configure their own experience.
Right.
And that's one of the things that's so exciting about being able to digitalize the human-machine interface.
And to me, the customization that you're talking about is huge. So you can have the simple geometry and structure, but you can have multiple looks. And that to me is something that is mind-blowing. Now, I know
Not just multiple looks, John. Because of the way this is made, you know, as Pavel was showing you, we are printing the electronics and we are printing the decoration. So as long as we stay within that same geometry, we can change both the look and the function. So if you had an entry level, a mid-level, and a high level, you could use the exact same tooling. So amortizing those costs over an entire set of series of parts that include different combinations of functionality.
exciting stuff. Exciting stuff for sure. One of the things that I know you cannot talk about, but let's talk in abstract terms. What's coming down the road? What has you excited the most about where your technology seems to be gaining traction? And we don't want to talk about OEMs. We don't want to talk about specifics.
Well, let's start about some of the feature cases. Clearly, capacitive touch and antennas perform extremely well. But I started out by saying, let light live. And while this isn't pointing to a single use case, it's pointing to a huge collection of use cases. One of the great benefits of our approach to this technology is that we are able to integrate the components within the molded plastics. And that creates the types of lighting effects that you've seen here. And they are very diverse and allow a huge scope of design opportunities that are very challenging with conventional technology. And one of the challenges with this approach, historically, has been light bleed, meaning not being able to isolate light and have controls really close together and make sure that they are very precisely illuminated. We have developed a methodology to both increase light output and increase uniformity while completely eliminating light leakage. So Pavel, we have another new lighting technology that's proving very popular with OEMs. maybe you can describe that at a really high level.
Yeah. So, John, consider, for example, a car door. There's an area, we can illuminate that dynamically with high light performance, which cannot be done with current manufacturing technologies out there.
Wow. That is cool. Looking forward to that.
Yeah.
I think that's a wrap, gents. Thank you so much.
Thank you, John.
Thank you.